Okay, so now we're going to talk about the Bohr model of an atom, which we'll find in this conversation is incomplete, but a critical step forward for physicists. All right, so Niels Bohr, 1913, he explained the emission spectra for hydrogen, which we described in a previous conversation, and he'd explain it in the following way, okay? Bohr's work convinced scientists, by the way. He convinced everybody to abandon classical physics, and he said, we need a new kind of physics called quantum mechanics, okay? So atoms consist, and here's the Bohr model. I'm sorry, prior to the Bohr model. Prior to the Bohr model, atoms consisted of tiny, dense nuclei surrounded by lighter and even smaller electrons continually moving around the nucleus, which sounds kind of like how we think of atoms today, right? This classical mechanical description of the atom is incomplete, since an electron moving in an elliptical orbit should be accelerating. And if it's accelerating, the electron should be continuously emitting electromagnetic radiation constantly, right? But we know that that's not true. So this loss in orbital energy would result in the electron's orbital getting continually smaller until it spirals into the nucleus and essentially annihilates, right? So we know that doesn't happen. We know that atoms are relatively long-lasting. We don't know how long, right? But long enough for us to be able to walk around and figure that, you know, if you build something, it's probably going to be there tomorrow, unless somebody tears it down. Right, so Niels Bohr attempted to resolve this paradox by he ignored classical magnetism's prediction, classical mechanics prediction, that the orbiting electron would continuously emit light. He said, all right, so that's not legit. I'm first of all going to assume that's not, because we know it doesn't happen, right? We see it doesn't happen, so that's not legit. So Bohr incorporated the following into the classical mechanics description of the atom. First of all, Max Planck had already suggested that that light is quantized, right? We saw that in a previous conversation. So quantization, in other words, we have steps. We don't have a continuum. So Einstein's found in 1905, 1906, he got the Nobel Prize in 1915 for showing that light consists of photons whose energy is proportional to their frequency with the photoelectric effect. Okay, big deal, big deal. Finding that light consists of photons whose energy is proportional to their frequency. No, that's not right. Proportional, right? Energy is proportional to their frequency, right? So Bohr assumed that the electron orbiting the nucleus would not normally emit any radiation, right? He assumed that because he saw it wasn't happening. Rather, the electron emits or absorbs a photon if it's moved to a different orbit, if it is moved to a different orbit, okay? So the energy absorbed or emitted would reflect the differences in the orbital energy. So if something's going from one orbit to another, here's the final orbit, the energy of the final orbit, here's the energy of the initial orbit, it's going to go a difference according to this equation, right? The initial and final orbital energies are here. Bohr assumed that only discrete values for the energy differences were possible, because that's what he saw, right? Bohr's expression for the quantized energies looks like this, right? Where n is equal to 1, 2, or 3, or more, right? K is a constant comprising fundamental constants such as electron mass and Planck's constant, and it turns out it looks just like the Rydberg equation. Wow. Just like it. Okay, so good news, good news. So figure 614 from your textbook shows that the energy here is 2.18 times 10 negative 18 joules. The energy here is negative 5.45 times 10 negative 19 joules, right? So this is the first energy level. Here's the second energy level. Here's the third energy level, here's the fourth, and here's the fifth, right? So, and he calculated what those were according to the equation which I showed you in the previous slide, okay? One of the most fundamental laws of physics is that matter is most stable when it's the lowest possible energy. So we're going to call that lowest energy orbit, n is equal to 1. We're going to call that the ground state. And anything higher than that is going to be called an excited state. When the atom absorbs a photon, it goes from a lower state to a higher state. And right when it falls back down, it emits a photon. Okay? And so energy, the changes in energy can only be discrete values. The photon absorbed or emitted can only have a wavelength with a discrete value, and that explains the colors we saw in the previous line spectra. All right, so if something falls from 2 to 1, boom, it lets off purple. I'm sorry, it lets off blue, right? If something falls from 3 to 1, it lets off a green photon, right? Something lets off a, right? You see that? Okay. So each of these, you can see those. These are emitting photons. These are photons that we see. Okay. And these are photons getting pushed up from the first energy level to the second. That's going to absorb a photon. Okay. Now there's some limitations with the Bohr model. This is going to bother you. It turns out that it only works with a hydrogen atom, right? And so at first we're going, well, my goodness, how much of nature is hydrogen and how much is other things, right? So how could this possibly be useful? Well, hold on to your hats. It is useful, but it does have it only works for hydrogen. But it's again, I'm going to convince you. I think it's a critical step forward. So it does not account for anything that has more than one electron, right? Which for atoms, not ions, for atoms, everything besides hydrogen has more than one electron. Okay. So it's also flawed because it bases its class of mechanics motion on precise orbits. That in other words, we think about electrons being in a particular very precise place. Okay. By the way, we very rarely does it matter that they're not. So we're mostly going to treat it like this is true, but it's not technically true. Okay. The Bohr model does introduce several important features that energies of electrons are in an atom, and they are described by particular numbers, okay? So the n's I was showing you earlier are numbers. They're integers, and that's going to be a quantum number that we're going to use to do other things, some more sophisticated things, right? And he also showed that electrons' energy increases with increasing distance from the nucleus, and that discrete energies or lines in the spectra result from quantized electronic energies, okay? So Bohr won the Nobel Prize in physics in 1922 for his contributions. It became clear to most physicists at the time that the classical theories that we typically are used to, that we can see and touch and feel in the macroscopic world, simply are not going to work when it comes to something, and this is even a sub-microscopic domain. Think super, super tiny and super, super fast. Need a new kind of physics that we are going to call quantum mechanics.